In this tutorial, we will present an overview of the CANbus physical layer. This tutorial will explain the concepts you need to understand the physical hardware of a CANbus. Understanding the physical hardware will allow you to assemble a CANbus yourself in a lab or on a bench and diagnose many common problems that customers have with their lab assembly. First, we will look at a simple view, and then we will dig deeper and look at a more detailed view. In the simplest terms, the CANbus has a backbone shown here in the diagram at the bottom. It has two 120 ohm termination resistors on each end of the backbone. The backbone is long compared to the short lengths between the backbone and a node. These short lengths are called drops. In a vehicle, the nodes are the ECUs, the electronic control units. This diagram is similar to a diagram that you'd find on the internet, such as the one on Wikipedia. However, this is not the whole story, and this diagram is missing some key features that are important for understanding the unique properties of the physical layer of any CANbus network. Let's look at a more accurate diagram to understand the rest of the story. The diagram you see here at the bottom shows a pair of wires in a twisted pair configuration with the usual 120 ohm terminators, just like we saw in the previous figure. The wires you see here are examples of twisted pair. You can also see the termination resistor that we used in our lab setup. Wires configured like this act as a special type of electrical conductor known as a transmission line. A transmission line has specific properties that make it ideal for use in communication applications. These twisted pair wires implement a specific type of transmission line called a balanced line. The balanced line transmission line has specific electrical properties that are necessary for the CANbus to function properly. However, the good news is that you don't need to solve any impedance equations to set up a CANbus. All you need to do is use twisted line and terminate at each end. The proper CANbus function depends on the line being twisted and terminated. This is true for dual wire CAN, which is also known as high-speed CAN. Single wire CAN does not use twisted pair. Another important property of the CANbus is that it is a differential signal. By differential, we mean that the signals are referenced to each other and not to ground. These signals require a differential op-amp receiver to receive these signals. So every CANbus controller chip contains a differential receiver. The picture on the right is an image of the scope trace of the CAN signals. Here you can see the individual CAN high and CAN low signals are opposites of each other. As CAN high goes high, CAN low goes low, and vice versa. The twisted pair combination with the differential signal is known as a twisted pair differential signal. The twisted pair differential has unique electromagnetic properties that make it extremely noise immune, which is a very good choice for use in noisy environments such as automotive. Noise immune in this case means that it can run well in a noisy environment. This is different from being fault tolerant, and for that you need FT-CAN. The twisted pair differential line has very high common mode rejection. By common mode we mean that in a noisy environment, noise will be induced on both wires the same way. This common mode noise can then be completely filtered out by the differential receiver. Here you can see an example image. At the top is a noisy signal, both lines. The bottom trace shows the clean output signal that is recovered from the noisy lines. This example shows that you can have an extreme amount of common mode noise and still receive a good, clean signal. Another common problem that engineers have when setting up a CANbus is that a CAN transmission requires a receiver to acknowledge the signal before the transmitter considers the signal is transmitted. In other words, transmission is not done until the transmitter receives an ACK signal back from a receiver. In this first figure, you'll see a transmit message go out from the transmitter, and then in response to the transmit, the receiver sends an acknowledged signal. All nodes on the bus except the transmitter will send an acknowledged signal. You need at least two working nodes connected to a CANbus in order for the CANbus to work properly. If the receiver is not connected, the transmitter will not get an acknowledgement and it will not report that it is transmitting. Be aware that you can configure a receiver to be in receive read-only mode. In read-only mode, the receiver will listen to the CANbus messages, but it will not acknowledge. This is a useful property for diagnostics tools, for example, that want to connect up to the bus and listen to bus traffic without interfering with the bus at all. The second figure shows this arrangement where one of the modules, in this case the receiver in blue, is a read-only module. The blue read-only module only listens, it does not acknowledge. The ACK signal comes from the yellow receiver on the bus that is not in read-only mode. Now see the third figure. Having a bus composed of only a transmitter and a read-only receiver will not work as an active CANbus. You can use this information to diagnose problems with your CANbus. When your bus is not working, verify that at least one receiver on your bus is not in read-only mode. To review, the CANbus are not wires. The network is a balanced line transmission line, a common configuration in communication systems. The line terminators must be at both ends of the backbone. The CANbus signal is differential and must be on twisted pair wires. We need at least 2 working nodes for the CANbus to work, and the receivers must not be in read-only mode. Now you have lots of details about the CANbus physical layer that will allow you to quickly diagnose common problems with setting up a CANbus on the bench or in a lab environment.